Hello all, good evening. We'll start today. Maybe you will wait for 4 or 5 minutes more. Let's see if other people joins. Okay, so we'll go today directly into the ADS tutorial section, and today we'll see how to design a power divider. And I guess you must have noticed I have posted an assignment for the next week. Okay, so your task is to design the branch line coupler provided in the paper, and I have attached the paper also there. You must follow that. Yes.
Where you have posted that in the Teams?
Yeah, yeah, sure. In the Teams only. Didn't you see the post? Assignment one. Anyone else have
Post?
seen it? Yes.
No, I'm not able to see where.
In the Teams only. In general, you will see there are many posts, right? One of the posts are the regarding the assignment. Anybody else here has seen the post regarding assignment one? Okay, so somebody has saw. So all please go through the Teams. I will be posting all the assignments and regarding documents there. Maybe I will show you the post only there. Let me see. See, this is my Teams window. You can see it, right? Yeah, I guess you can see this same window in your Teams. So there, if you see, here I have posted design assignment one, deadline 5th June. Okay, that is next Sunday. So here I have given you, provided all the necessary instructions and as well as the paper required to study and design. Who was it? Ganesh. Yeah, Ganesh, can you confirm? Can you see this?
See that I'm able to see that right now your screen, but
Mm-hmm.
I'm trying to find out where it is there. Let me see the
Yeah.
activity.
Okay, okay. So you must be seeing the same things here, what I see. And other people also confirmed. Yeah. Can anybody else confirm?
Yes, sir. I am able to see as well.
Okay, okay, okay. Yeah. Okay, so all please go through this and let me know any questions are there. Okay.
Sir, hello.
Yes, yes.
Sir, chat section is not enabled for me, and I can't see this whole chat and this assignment and all the things. It is not enabled for me. Chat one.
I don't know. Did you register for the course or not?
Yeah, I registered for the course. That's why I got the email notification
Mm-hmm.
to as a meeting in my Teams channel, and then I joined the this meeting through the Teams only.
Ah, okay. So then you must have any problem in your side because it's same for the others also, right? So see, change your any settings or something is required maybe. Okay. Yeah, I can do anything from my side because from my side is open for everybody, right?
Okay, so
Apart from that, this will be also available in the portal, right?
Sorry, which portal?
IEEE portal.
No, 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 no. That does not have anything to do. That is just hosting the link for the lectures and all. Nothing else.
No, no. Those who are registered, their
Mm-hmm.
lecture notes will be available in the portal, where we can go and see that portal also.
No, 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 no. For that only I have opened this Teams. You will get all the necessary instructions and resources only here, only in the Teams group. So anybody else here are getting it? Somebody, one guy said,
Uh,
yeah.
let me check, log out and check out once.
Uh-huh, yes, yes. One guy said, and
yeah.
anybody else? Yeah, yeah.
This is Sam. Actually, I have registered for. I got the email for this link one, my Teams link. But the thing is that I cannot able to open this one, like Teams account, with my Gmail ID.
You cannot open means you are not seeing anything there?
Yeah.
Like sort of like for other meetings for the teams, I can, this chat section is there, but for this only this meeting the chat section is not there. Like we chat some PDF we share. For other meetings it is there, but for this meeting only from yesterday onward, yesterday the class starts, so at that time as well this the chat which you showed, it was not visible to me. Like in the top of that, the take control pop up people, so at that point, at there the chat section is there, so but in this meeting it is not visible, and that's why after attends nothing I got like chat and all in
No,
my
no. See,
team.
chat is not required or anything because I will be posting all the things in the team. You can access if you can access the teams, then it is fine. Yeah, chat is not a big deal.
No, I can access the Teams, and this meeting is from the Teams only, na. So, but this group that you created, design and simulation of RF circuit. So this group is not visible to me. Like you post something, you post something there, so it is not visible. Only I can join the meeting from my Outlook because I installed this thing. I installed this file in my Outlook, and in my Teams it got registered, so it gives pop up like at 5:30 you can join the meeting, so I joined the meeting using that, but this chat is not there.
Okay. So I also have no idea like what is wrong with that. You maybe suggest something. I will see. You look into or maybe talk with others and let me know if I can do anything on that. Okay.
Sauro, I think we have used our Gmail ID to register, but
Right.
thing is that we need to give our either our Outlook or Hotmail to access this one. So the email accounts are different. So maybe we could not able to see these things. I hope so.
Okay, that I also don't know. Yeah, might be some solution. Yeah.
I will email my Hotmail ID or Outlook one. So
Yeah. Sure. I will add that. Yes. Okay.
yeah.
And somebody raised hand. Who is that? Yeah. IUC. Yes.
Yeah. Yeah, sir.
Hmm.
So same problem is happening with me also. So my chat is also disabled. I am also only able to join the meeting. So I am logged, like my personal Gmail ID is there. But yeah, I think Outlook is not, like that account is not there. So that's why I'm also not able to see any content.
Yes.
Okay.
I
So
think
somebody
this is the main problem. Like I
maybe.
registered using different email ID, and my
Hmm.
Outlook is registered with my office ID. So
Hmm.
I think both of them are different. That's why I registered using my personal ID, and it is not showing here. So it
Hmm.
might be the reason. So
Yeah. So somebody said that Outlook mail IDs work. So you may, ping me or you may mail me with your Outlook mail that I will add to the Teams. Okay.
okay,
You might.
okay,
Okay.
okay.
Yeah.
Yes.
Yeah. So somebody said who was that? Juginder. Juginder, can you confirm? Can you see with Gmail ID or Outlook ID in the Teams?
Gmail ID only. Same issue is for me also.
Mm-hmm.
I have registered in my Gmail account, but my official ID Outlook was been configured to get the meeting.
Okay.
And right now I'm not able to do. Shall I give my official ID so that it will be easy to configure?
Yeah, you give me any mail ID, I will add it. I don't have any problem for that. But somebody
Oh,
got it. This is Ganesh, right?
yes.
Yeah, but I want to know from somebody who can access the Teams group. Who is that? Juginder?
Okay.
Yes.
Yes, sir. I can access the Teams group. What you want actually? I have received the assignment also.
Are you accessing through your Gmail ID or Outlook ID?
Yes. No, Gmail only.
Yeah. So that's why, I don't think it will be a problem for Gmail or Outlook. I don't know why others are not getting because it's same for everybody, right? Yeah.
So one more thing, today morning session class was there or no?
No, I told you, no, yesterday the classes will
Okay.
be only on the afternoon. Only when some extra classes are required, then only we'll go to morning session.
Okay.
Okay, so with that, any more question? Otherwise, I will move to the tutorial.
Sir, one more thing, it will be far better that if we create some WhatsApp group link so that we all get connected on WhatsApp only, so that we will get continuous update of regarding classes and assignments and all that.
See, WhatsApp group will be a problem because we don't know everybody's phone number and all, and it might not be feasible. You might create a mail group or something that might be possible.
Uh,
Okay.
okay.
No, while registering, we have given our phone numbers and email ID. Previously, when I attended all this ICS course, there used to be a WhatsApp group where you add all the people and messages
Yes, yes,
and
yes.
doubts will be cleared.
No, so that is
Yes, sir.
there, but I cannot, add everybody in a WhatsApp group unless everybody,
So, sir, we
yeah.
will create some WhatsApp chat link, na? So, just a single link by clicking onto that one.
Okay. So
The
you
whole,
guys, whoever has the link, please post it in the Teams. So I will maybe in the message only you can create and now post in the chat so that people will join. Okay. Then I will join and
because
post the assignments there. Okay.
because something is likely to happen. I even cannot access the chats and assignment that you have posted. The only window that I am seeing is your that PDF file is over there. I cannot say anything what you have
Okay,
posted over
no
there.
problem. Yeah, you create a WhatsApp group and now only you post in the message here in the during this video, during this this thing here, and then people can join
Okay.
whoever wants. Okay.
Okay. Okay.
Yeah. I think you can see the chat window here, right?
No, I'm also not able to see the chat window as well as I cannot type the chat. I'm not seeing anything over there.
Okay. Okay.
Sir,
Somebody has,
sir,
yeah.
sir, you sent an email on 21st of May. On the from the ID was registered. You sent in that email. You sent the form link. So it is written that if you're not on the Teams group yet, then please fill out the following form. So do we have to fill that form? Then we will then our chat will be enabled. Is it same?
No, nothing. You can try that. Who has
But that
already?
form is closed. That form is right now
Yeah,
closed.
that form is closed because thought everybody else is already registered in the Teams, already included in the Teams. So I
Okay,
did
so
not. Yeah.
so I just email you my email ID on the same
Yeah.
email
You
which you
you
sent.
try once that also and create a WhatsApp group also and then circulate and let me know. Okay. Yeah.
WhatsApp group I think it's not possible because we don't know the phone number of everybody.
No,
So
we'll post it here, and whoever wants to get themselves, they can add themselves by, as somebody pointed out that by just clicking on the joining link, they can add themselves. Okay, it is up to them.
Yes, yes. WhatsApp group link. We will create
Yeah.
that one.
Yeah, somebody create the WhatsApp group. I will post it here and in the Teams. Whoever wants to join, they can, click and join on that. Okay.
okay.
Hmm.
Sir, I will create that
Also,
link. I will mail you because I'm not able to see the chat window over here.
Yeah. Okay. Mail. No problem. Yes, somebody
Okay, sir.
else.
Okay.
so sir, this WhatsApp group can be shared through mail only because our chat window is disabled. So if that is posted in chat, then I cannot join through this
Okay,
team group.
see, yeah, that is also there. That is there. Okay, I will try to maybe send a WhatsApp link also through mail to everybody. Okay.
Thank you.
Okay. See, the somebody has posted here. This. If you can see, I don't know. Can you see this? Maybe I will download. Somebody like Swastik has posted some solution. Let me see. Let me share this with you guys.
Sir, one small request, sir.
Yes, yes.
Sir, the videos, the yesterday's session, so we were able to see only while we logged into Teams. So is there a facility to review it offline, sir?
No, no, that I have no idea. You have to download it or something like is possible. So,
Download yes, sir.
just a minute. See, somebody posted a picture with their screenshots. Can you see it? So he posted that he faced the similar problem, and you have to change this thing here as a guest, Indian Institute of Science guest. This thing in the settings you have to change. So then only you will be able to, see this. Let's see what he posted here. Who was it? Sastik. Yes. So he posted that check here if you have if you are unable to access. So he is saying you have to change this thing here, Indian Institute of Science guest. This you might have to change something like this in your settings, Team settings.
Yes, sir. While logged in, it will ask for either personal or IASC site.
So I guess, see, these people are doing, so you might maybe also able to do. Okay. Okay, anyway, see, we have to move on because these things will be there. Always some problem would be there, but we have to move on.
Yes, sir. My request, like whether we will be able to access the videos offline. Is there any?
No, as of now, it is online. You do it online. Offline, I don't know. I will see if you just see if download option is there. You try. Otherwise, we'll see it later.
Okay, sir. Yeah, as of now, there is no download option.
Okay. So I will see. Okay.
Yeah, sure, sir. Thank you.
Yeah. Okay, so we'll start now. So today we will go into the basics of ADS tutorial. Okay. As I told you, I will follow the ADS software from Keysight, and you might follow any other software like AWR and somebody said Multisim, whatever you find comfortable yourself, and you can try that. But the learning you have to do yourself, right? Okay. So the basics or the basic features of ADS is you can do RF simulation like microwave simulation as well as signal integrity simulation, as well as you can do circuit simulation. Okay. So together you can do both EM electromagnetic and circuit co-simulation, that is in a single tool. Okay. And there are separate various different simulators available like harmonic balance, circuit envelope, and X parameter features, all this. There are 3D EM simulation tools. So 3D in the sense like, you can do a full wave simulation where you can calculate electromagnetic fields. And the simulators are like momentum, which works based on method of moments, and FEM and FDTD. Okay. So basic application, definitely, all the RF and microwave things you can simulate and see how they will actually work. And as you know, these simulation tools are very good. All these tools like ADS, CST, HFSS, they're almost like so good that if you simulate and see in the actual measurement, they matches quite very well. Okay, so that is the beauty of these tools. So that's why we do the simulations first, and then we do the actual design, hardware design, right? So okay, and so what are the different simulators available? Simulators means there are different facilities available for different type of circuits, different type of simulations. So depends on what actually you want to do, what is your objective of design, right? So obviously the basic thing is linear frequency domain solver, where you will have linear circuit simulation. You can do S parameter simulation, voltage, current simulation, all this. And there is harmonic balance simulation. So this harmonic balance is a very vital part because with this you can do nonlinear simulation, like where you have amplifier, mixer, oscillator, diode, all this. This thing you can actually do nonlinear behavior simulation. You will do through harmonic balance. And there are X parameter simulation. So X parameter is, what is it? Is the extension of S parameter. S parameter is basically a linear tool. Okay. A linear parameter, because you give some signal, you get some signal in the other port, right? So it is, if you see the equations of S parameter, it is basically a matrix equation. And matrix, as you know, those are definitely linear. Now the thing is, oftentimes in our simulation, we'll have not only a single carrier component, but we will have the harmonic components also. Like let's say we have a 4 gigahertz carrier, but because of the hardware impurities or imperfections, or the imperfections in LO local oscillator, it will generate multiple separate harmonics, right? So for that, you will have power in the other frequency, nearby frequency components also. To simulate that, X parameter concept has been given. Okay. So that is there. This is just to see nonlinear behavior of components. And there are 3D simulators like as I told you, Momentum, FEM or FDTD. All of them are very good, and you can do through these 3D planar circuits, and all the arbitrary 3D geometry. If you can produce the geometry, create the geometry structure, or even you can import any 3D structure also in here using Gerber file or STL files, and you can simulate that through a source. Okay. And there are electrothermal co-simulator also available. Okay. Because the thing is, you can do oftentimes all our hardwares, because it may work on high frequency circuits and all, and as well as high power electromagnetics, you might have to see how much heat is being generated in the circuit. In that case, electrothermal co-simulation is required. So that opportunity, that option is also here in ADS. So now the question is why 3D simulation is required. Okay, so people might say, why not we do only circuit simulation? So which is called schematic here in ADS. So why that is not sufficient? So the main reason is that the whatever circuit you have design in schematic, that may not be idealistic. They might not be realistic. Okay. So the circuit in the actual hardware design, when you see, there will be traces or PCB traces there, and there will be even the cuts and bends and all those things, and there will be actual substrate, there will be via, and all these components will lead to some parasitic things. Okay, and there will be coupling between them. So all these things are very difficult to capture through some equation. Okay, that's why nowadays we use 3D simulators, 3D EM simulators like CST, HFSS, and now even in ADS. That's why this 3D simulation is very vital to actually. So if you do 3D simulation, then only you will actually know what the results will be, what the simulation results will be, because circuit simulations are often not, will not match with your hardware design. And that's why a integrated design model is required, where you take care of all these things through combined electric and magnetic field simulation. Okay, which will take care of all the mutual coupling, all the parasitic effect, everything. And what is, it kind of creates like a virtual chamber. Virtual chamber means anechoic chamber, where you have some boundaries. Inside that, you do the simulation. So there will not be any interaction with the outside world also. So it will be only the simulation with your circuit itself. Okay. So that is about 3D simulation. So now we'll go into, start the simulation flow. So what is this flow? So first we design a schematic. Schematic means it is just a circuit components. So in ADS, you will have like, small microstrip line components available. There are various other components like bend and T and all this. You have port termination available, and you have, grounding, sorting, open, via, all the defined components you can imagine in electromagnetics. Most of them you will find in their library. Okay, in ADS you will have a circuit library, and you will have a the component library, transistor library, diode library, microstrip library. So through that you can fetch different components and then build a circuit. Now in the schematic, so I guess they will have a underlying equation there running there. Whenever you run this S parameter equation, you can see the S parameter results only in the left side schematic only. Okay. But as I told you, this is not a 3D simulation. So it will not be a ideal realistic results. So that's why you have to move to layout. So see in the middle, I show you the layout, which in the middle it shows if you transfer this schematic to a actual 3D design, how it will look. That is called a layout. Okay. So in the middle, you see this as a layout, which shows the metallic stresses on a substrate board. And now you can do a 3D simulation on the layout. Please shut down your mic, please. Yeah, and now the thing is, but it does not stop here. Oftentimes, you will have many lumped components like diode and even capacitor, resistor, inductor. All these components you cannot include in the 3D simulation. That you have to take care of. Okay, so 3D simulations you cannot include here in ADS. So that's why the feature they have is called co-simulation. So once you have the layout ready, then you can add the resistance here. As you see in Wilkinson, we'll have a resistance or all the other lumped components like you see in the right hand, left hand side. I have the port terminals. Once you add them, then you can do a simulation once again, S parameter simulation. So that's why it starts from schematic, goes to layout, and then finally again you add your lumped components and you can simulate. It is called co-simulation. Co-simulation means 3D simulation as well as together as lumped simulation, lumped components. That's why it's co. Now you see there are various different components available. So some of the important things for our microstrip design is some of them are like substrate. Definitely first thing you have to include in your simulation is substrate. So substrate parameters has thickness and the relative dielectric constant, and then you have conductor thickness, which will be like around 18 to 35 micron, and then you have loss tangent, tan d. Okay, so these are the vital parts. And as you see here, it does not look like a normal substrate. So because they have generalized the design, it can be even done for strip line, micro strip line both. So in the strip line format, you can have a
Sir, your voice is breaking. Can you speak little louder?
Yeah, is it breaking for others also? Yeah, can others confirm? You can. Fine, right? So I guess you can log out and log in again. You might have some internet issues. Okay, so yeah, so that's why they have a very generalized substrate which can be used for both strip line and micro strip line. Okay, in case of strip line, as you know, the conductor or the metallic patch will be inside, and both side you will have a substrate as well as ground layer. Okay, but we don't go into that. In our case, we will have only microstrip line. And now we have a MT microstrip T. So why this T line is there? Because most of the times we will have a junction of various different lines. Okay, so that's why this MT is there. So and this MT is very vital. So you can define the width of the three times. 1, 2, 3. You see, those are defined, and you have to define 1, 2, and 3 line widths. So those are nothing but the top metallic conductor, and how you distribute the widths will depend on, but based on that you can connect multiple lines through this MT. In the third section we have M curve. So sometimes, as you know, a very sharp bend can create problems in your design. It can raise to extra parasitics as well as it can radius also. So oftentimes we create a M curve, and sometimes it's called chamfering or tapering or metered bends. So these M curves are also very handy here. You can use those just by just by defining the radius. So these are three components, and you have like plenty of different components. You can just go into help and I will show you that also. Okay, so before I go to Wilkinson power divider design, I will open the microstrip line. Sorry, I'll go into ADS window. See, this is the ADS window you see. Once you open, you will get a window like this. Okay. So in the corner, you can create a workspace. You see, whenever I open this, it shows a new workspace widget. So you click it and you can create a workspace name. Let's say I name it ADS tutorial. So I name it as this way. And there are these libraries. By default, ADS libraries are included. So you can include this. Later on, there will be required for, passive circuit or like transistor libraries will be required. That I will let you know later. But for now, only ADS library is fine. So it will create this library inside. And see, the vital part is it will tell you like which kind of layout you want to define. So if some of you are working with ADS, you make sure that you select the first option, this 0.001 mil layout layer. Okay. So you might work with others also, but for now our basic design, this is sufficient. Otherwise, I saw some of the cases it was creating some problems regarding port. If you don't select that, you might run into other problems. Okay. So select this mail layout resolution. Now next, we'll go next and then finish. See, you see, now we have created a open window, right? Now we'll go into a schematic. You see here, this is schematic, layout, and symbol. These three windows are here in the top. Okay. And there are plenty of other options you see here. File, you can, import and export options are there. You can import from, let's say, ADS, HFSS, CST, HFSS, all these things you can import here. You can import Gerber file and all. And as well as the export option is also there. You can archive, unarchive things. Means if you have a ADS project from somewhere else, you can unarchive and open here. Okay. And you have other options as well. You see, you can just go into this and you will see lot of options inside. They have some design guide as well as some built-in solved problems already available, and you have a help toolbox also. Now the main things what we want is schematic and the layout. Okay, these will be used for design. And this data display window is where we'll see the results, is parameter simulation results. So first we'll click a cell. They call it cell. Inside you new project you have created, you will generate a new cell. It's okay. Okay, now you see we have a schematic window here. Right. So at the left side, we have a component palette. So I told you, we have different types of libraries available here. You see, we have transmission line, ideal transmission line options available. We have microstrip transmission line available. This is what we will be mostly using this. Okay. And there you have, the DC simulation components, lumped components, various different resistor, capacitor. So all these things you can see from this palette. Okay, you can just click on it and you can see what are the things. And here as well as you see there are different simulation options are there. DC simulation, time domain simulation, frequency domain, HB means harmonic, simulation S parameter. That is what I will be using mostly. Simulation S parameters and simulation HB. Okay. Simulation LSSP is large signal simulation. That also we'll see later. But there are all different kinds of option available. You can explore, look into that and explore them. Electrothermal, X parameter, all these. Okay. You can do plenty of things here. And I guess you will have the same option available in other softwares as well. Okay. So now what we are interested in microstrip line design. So what we will do, we'll select here transmission line microstrip. Okay. So now here, I hope you can see my screen, right? All are seeing, right?
Yes, sir.
Yes,
Okay.
it is visible. Yes, it's visible.
Okay. Okay. Sure. So see, first thing what we need is a M sub, as I told you. This is the microstrip substrate, what I was showing you. And anything, you can just double click on it and go to help. See, they will show you what are the parameters they are defining. You remember I was showing the same thing here in the PPT. So they define all the defined components what they have. So you might not need all of them, but the point is everything is available in help. You just have to double click on it and you can go into the help here. Okay, so that is how you can look into this. If you want to learn properly, you should see on the help. Now see, this substrate, let's say we start with a FR4 design. So we'll define the parameters here. Okay, so FR4 H, see, another thing is you should always notice about the dimensions. Okay, on the the units. Here you have millimeter, micrometer, centimeter, all kind of options are available. So you have to be careful there what you want. You have to always tick. Let's say I want a substrate thickness of 1.57. Okay, generally it is like either 0.08 millimeter or 1.6 millimeter. So I want a 1.57 millimeter FR4. FR4 I am taking, generally it is around 4.3 is the permittivity. There is no unit, so none. Okay. MUR is epsilon, relative mu, relative permeability. That is one, no problem. Conductivity is nothing. HU you don't have to change. What you have to change is T. T is 35, not mil, it's micron. So generally metal thickness or the top metal layer thickness is either around 35 micron we take. And the tan D, okay, tan D will take as 0.025. Let me see once again, confirm here. So these all you might have, question like why, how we get it. So if you just search in Google or you search in the data sheet of the substrate you want to design for, let's say Rogers and all, they will give all these things in details. What are the permittivity, loss tangent, or they will have all other components also available. That also you can put. But for now, we will need all these three things now. H, substrate thickness, ER is relative permittivity, and tan D is 0.025. Okay, apply. So if we apply and it shows like that, and we will name this also, let's say, okay, M sub 1 is fine. Okay, so that is fine. Okay. So now our substrate is, first thing is we select the substrate because all the design will be done on some substrate only, right? So that is the first thing. Now we'll move into the other components. Before that, yeah, so our main goal is, designing this Wilkinson power divider. So if you have gone through yesterday's class, so we have 3 ports here, right? And if you remember, among these 3 ports, we have this 2 quarter wave line, which has a the characteristic impedance is root 2 Z naught. That is what we have calculated yesterday, right? So root 2 Z naught is the characteristic impedance and length are lambda by 4 and the resistance connecting them is 100 ohm. So that is the design, the main parameters. So now what we have to do is we have to calculate the line width. See in the middle, we have to know what are the main design parameters. For a 50 ohm line and root 2 Z naught is 70.7.1 ohm. For these two lines, we have to see what is the line width. Because once the substrate is fixed, only what we can change is the line width, microstrip line width. Okay, that is what we will calculate. And the length of line lambda by 4. Length also because our electrical length is lambda by 4. So we have to see how much line length is required. That we will calculate. Because as you remember, that will depend on the effective permittivity, not on the just epsilon r 4.3. So those things we have to calculate. And how will we do that? Yesterday, if you remember, I told you there are some internet tools available in some websites like EMTalk and all this. You can follow that. But ADS itself has a built-in line cal tool. We'll follow that. We'll go inside that now. Okay, I'll show you how to do that. So yeah, before going into this, so do you have any questions now? At this
Sir,
stage?
actually one doubt. When you have created MStub, right?
MSub, yes, right,
Yes.
yes.
MSub, in that it has seen we have seen that it is a strip line.
Strip line, yes, micro strip line.
Okay, strip line and micro strip line. No, but when we see the construction of that, it is showing.
No, see,
yeah.
no. That's why I told you, no. There are all other parameters here. Those I am not defining. If you define all those, then it will become a strip line. But for now, it is a micro strip line.
Okay, same thing can be based on giving our configuration. It can be a strip line, micro strip line, or anything. It can be.
Yeah, right. Okay. Because they have a generalized design. Yes.
Okay, sir. Thank you.
Yeah. Anybody else?
Yes, sir.
One by one, please. Yes.
Sir, this MSub is defined for the PCB, right?
Defined for the PCB, right? Yes.
So, sir, we can. So, if it is not mandatory that MSub is defined in the ADS, is it compulsory to define MSub in the ADS, or if we don't define, then is it okay?
No, you cannot design, right? How can you design a microstrip line without a substrate?
Okay. But this is actually for PCB, right?
This is for a microstrip line design. You can really PCB or substrate, whatever you want. Yes.
Okay.
Yeah. Next.
So, sir, I want to ask, like, suppose if we don't define all parameters here, and let's say if we define any Rogers substrate, this conductivity and HU, will it make any difference or any effect?
Yes. Let's say you have a Rogers 5880 duroid substrate. So you have to define the whatever you have height, substrate height, permittivity, and tan delta. All of those will be different. Okay. So, but that is not the main thing. The next thing, for defined substrates, the line characteristics will be different. For a 50 ohm line in Rogers and 50 ohm line in FR4 are very different. So those line width you have to calculate using the line cal tool. That is what I'm coming next. Using the tool, now for your defined substrate, you have to calculate.
Okay. Thank you.
Yes. Next.
Sir, can you go to once back MSub?
MSub, yeah. Yes.
Sir, in this, if we see the conductivity, COND means conductivity, sir.
COND is it's a conductivity for the ground layer, because it's a perfect conductive layer they are taking. Okay, is very high.
So based on materials, this thing also will be changed, or it is fixed?
No. So that's why I told you, these things, there are many other parameters available. Those you don't have to generally see. Okay. So only required parameters for microstrip line design is H, ER, M, and T is the metal thickness, and tan D. Okay. Yeah.
Okay. Four things are sufficient.
But yeah, if you are really interested, you can go into help and see. See, they have listed so like 20 or 30 defined parameters. You can look into those. Yeah.
Okay, sir.
Sir, when you have created this workspace, very firstly you had to ask us to select that the mill resolution 0.0 mill resolution, and then later we are going to change the units from mil to millimeters. So instead of doing that, if we are going to select directly that resolutions to be in millimeter, so I guess there will be no need to change these dimensions from mil to millimeter, isn't it?
No. See, no. That is just the underlying method required. But once you take these components, they are completely different.
Okay.
You have to define the units here. Whatever you take outside, that does not matter with it. Here you see all the defined units are there. You have to you have to separately select this.
Hello. Okay. So
Yes.
because I have faced that problem, I have started my some design in starting with that mil resolution. Then I forgot to change that dimension, so I got wrong simulations for that. Okay, it's fine. Anyways, it's fine. Thank you, sir.
Yeah. Next. Yes.
Hello. While we are taking RT Joyride for this design, in real time we will do gold plating, na?
You will do gold plating where? No, no. See,
On the Sartidurate we will do gold plating actually in real time.
No. See, I have not seen any design with gold plating. You might do to reduce the loss and all, but
Yes, yes, yes.
yeah, it's not mandatory.
How can we do then conductivity everything according to that only we have to design, na, actually.
So you are saying gold? How to take that gold thing?
No, not. While we designing, only we will take that articulate only. After that, while implementing, after we will put in jig, we will make it in gold plating, na, 1 mm thickness.
Yeah,
For conductivity, pure conductivity.
Yeah. That
on the articulate sheet only.
But here only you see substrate. We are taking the conductivity very high. This is very close to perfect conductor. So it will not matter in whatever you plate, gold or silver or any other thing. It will not matter much.
It's not that it not affect.
Because we are taking is yeah, right.
It is not affect to design and our practical purpose.
Right. So now, okay, now we'll go to the line cal tool and see how to design. Okay, all please switch off your mic. Yes. Okay, see inside tools you have the line cal tool. Okay, so start line cal. Who is it? Okay, so now see for line cal, the substrate is there, and again we have to define the permittivity for which substrate we want to calculate. So our goal is we have two lines, right? One is 50 ohm and another √2 into 50, that is 70.7 ohm. For these two lines, we have to calculate what should be the line width. Now see, E and mu we have defined, and mm we define how many millimeter? 1.57. T, let's say we take as 35 micron. And 10D we take as 0.025. Okay. And now let's say we want 50 ohm. Because we want 50 ohm line, we want to design with this FR4 substrate. And E effective, we will have to see how much. Okay. Let's say this we defined as millimeter. So let's see. And effective length is lambda by 4 is 180 degree. I mean electrical length. Yeah.
You have not changed the frequency over there.
That is fine, but yeah, right. Let's say I take it for that's a good point you have noted. Let's say I do it for 3 gigahertz. Okay.
Yes.
So now you tell me how frequency is relevant here. If I don't select the frequency, what will be the problem?
Nowadays frequency dependent, no, sir.
Yes, right. But for impedance calculation, characteristic impedance calculation, it will not vary. It will not change much. Okay, it will be almost like nearby frequency will be same. Only for effective calculation, effective length calculation, it will be required. Now let's see.
Okay.
Yeah. So lambda by 4 is 180 degree we take. So we want to calculate is you see here W and L. These parameters you see note here. W is the line width and L is the length of the line, microstrip line. That is what we want to calculate. Now see, we do synthesize. It takes some time and calculates. So what does it say?
Sir, one doubt actually for 50 ohm we don't require any
once a minute, sir. Let me complete, then I will take the doubts later.
Yeah, sure, okay? Sure.
Yeah. So now the thing is, See, we have designed the line here. So what we get is width of W of 3.36 line width millimeter and length is 8.08. Lambda by 4 line length will be 8.808. That is how you calculate. If you see here, W and L, it is calculated. I have calculated for 50 ohm and a 180-degree line. Okay. Similarly, we'll calculate for 70.7 ohm. So see here, it is 1.8 is the line width and 8.35 millimeter is the line length. Lambda by 4 length of 70 ohm line will be 8.35 millimeter. Yeah, now you tell me who has a question. Yes.
Yes, sir. Actually, for 50 ohm also we require this lambda by 4 length.
Sorry?
No. Actually, for 50 ohm also we required lambda by 4 length, sir.
Yeah, no, not for. It does not depend on 50 or 70. It depends on the design what we want to do. If you remember, we want to design a microstrip line, right? So we need two type of characteristics. One is Z0 50 ohm and another is root 2 Z0. That is 70.7 ohm. That's why we are calculating this. Okay, so next move on to next. Let's see.
But
so
length
now
is not required, na, sir. Means lambda by 4 only means root Z0 into root 2 is only lambda by 4, na? Input is not a lambda by 4.
Input which? No. Come again?
No. For power divider, input is 50 ohm. It is like a normal 50 ohm track. But when we go to port A and port B, it should be lambda by 4 line.
That's fine. Oh, you are saying the 50 ohm line length is not required. That is what you are saying?
Yes.
Okay. No, I am just showing here the calculation. If you have to calculate, how you will do. Okay. Yeah.
Okay.
That is right. Yes, that is right. So now, so the thing is, as somebody pointed out, I did it for 10 gigahertz. But let's say I want to design for 3 gigahertz. What will it be? See, for different frequencies, you see now how much it changed. The line length for 70 ohm, it changed. It is 1.6 now and 28.51. Separately, so 1.6 and 28.51. And let's say for 50 ohm now. Yeah, just a minute. Oh, so yeah, sorry. I actually did a mistake here. It is like lambda by 4, that so it will be 90 degree, right? But you did not point out that it should be 90 degree, right? It's not a 180 degree line. So those things you have to look into carefully. So it will be 3.06 millimeter, and line length will not matter much. And for 70.7, you get 1.6 but 14.25. So these two, let's say now that we have calculated this, we'll move on to design. So yeah, so the thing is, you see all things you get here in tools. In tools, you can find the line cal. Here you can calculate. Now what we will take? We will take some variables here. Yeah, variables is required, but even without variables also, let's see. We'll take a simple microstrip line here. M-line. We take another M-line here. We take one M-line here. Now, yeah, soon it will be clear why we require so many lines. Let's see. So all the substrates are same. You see this M sub, all are M sub 1 linked to what we have already defined. Okay. So first one is this is a 50 ohm line for port 1. For a port 1 line, what we will define here is this, what we have calculated. What will be width for port 1? We have calculated 50 ohm line millimeter 3.06. Okay. Length is, we take generally, let's say lambda by 10. So, so lambda by 4 we calculated as 13 millimeter. Let's take lambda by 8. Let's take around 6 millimeter, or yeah. Let's take 10 millimeter only. It's not a big deal. You can change the port length and see how it changes the impacts you are matching. So this too, so the microstrip line will be defined as I told you on the width now, because substrate is defined now for everybody. Only changing the width, you can change the characteristic impedance. So because we have calculated for 50 ohm line, 3.06 is the line width. That is what we have defined here. Apply. Okay. This is the port line. Okay. Now, these two will be 70 ohm line and lambda by 4 length. So here it is much more vital. Let's say we take it here 1.6 millimeter and length we take as 14.25 millimeter. That is lambda by 4, or 90-degree line we have calculated from the line cal. This length is very vital. In the previous case, port length is not so important, but here, we have calculated before, we have seen that it has to be a lambda by 4 length. So that is what we define here. Now, here also it is a same thing, and even we can just copy paste this also. Let's say Control C, Control V. Right. And these lines also are 50 ohm lines, port lines for port 2 and 3. So we can just copy from this one, Control C, Control V, Control V. So what happens, this TL1 and TL6, these two are 70.7 ohm line, root to Z0, and length lambda by 4. All the rest of the lines are 50 ohm. So those are just required to connect to the ports. Okay, connect to the ports means your SMA connector or coaxial cable. Those are required for those connections. So now what is required? Let's say we just make a simple line connector. See this here on the top bar, you see all the different options are available. I am taking from there. So there you can define a variable, ground, port, and then you have the insert wire. This wire I am using. Okay. And there are other simulation options, tuning option, optimization option, lots of options are available on the top palette. Now for now I am using the insert wire. You have to, see, you have to just connect on the red dot here. So you have to be, careful here and put it to this one here. Similarly, you take another wire here. See, now you see, if the connection is done properly, you see the red becomes blue here in the middle. Otherwise, it will show like red. So that you have to be very careful. If somewhere some connection is not done, it will still show as red. Okay. So now our main work is just to see here, you see the connection I have not done purposefully to show you. See, it shows 2 red dots, but in the other end it shows as blue dots. So this end the connection is not done properly. So you have to reconnect it. Okay. So now that those things are done. Now what else is remaining? You have to connect the ports. Okay, before going that, we will take the lumped component. If you remember now, there is a 100 ohm resistance in between. Let's say I take this resistance here. I can rotate it.
Shift R.
Shift R, yeah.
Shift R.
Shift R, yeah. So generally, just clicking on it also it
Try
will
with
be
Control R. Control R. Control R.
Yeah. Yeah, right. So the resistance is there. Now it has to be connected between port 2 and 3, right? Let's say connected here till here, as well as connect till here till here. So this is the simple Wilkinson power divider design. Okay. So this 2 lambda by 4 length, and there is a resistor connected in between 100 ohm. I'll change the value to 100 ohm. And the ports. Now what is not done till now, how do you link it to S parameter simulation? For that, we will go to this S parameter model here, and then you put terminators. See, these are the terminators. So this terminator by default, it defines which port is. This time number is means what is the port number. Okay, that you be careful. So that's why how I have taken in this order. I have taken this as port 1. This I have taken as port 2, and this is as port 3. So within this simulation S parameter palette, you see, I told you, no, there are different things. I'm using simulation S parameter here. Inside that, you will have the terminations 50 ohm, 50 ohm, 50 ohm. Now you can connect a ground because all of them 50 ohms has to be grounded. Grounded, done. Now what is left is simulator. What kind of simulation you have to do? That is what you define here. Okay. So see, this S parameter by default, this is like a simulation machine, which will do, you can define a start and stop frequency. Let's say I take here 2 to 4 gigahertz. And let's say I take a step size of 0.01 gigahertz. Okay, that means 100 megahertz. Yes. So this linear start, step, and all these things when you define, you see it comes here. S parameter model. This is what will be doing the simulation. After defining your model, you have to do start, stop frequency and step. Step means at this intervals, it will create you will show the results. So now let's say all these things are done. Okay, let me just verify once. 50 ohm. Okay, let's say all there is done. So this point you have to click here, simulate. When this is done, it will done. See, it is done within a second. It shows simulation is done, total time and all this. If things are done properly, you will not have any message. And sometimes you will get some warning message, some error message. So that's why this window is very vital. Before going to this left side results window, you should see in the message window, what are the messages getting created here. Okay, it will give you what are the problems in your design, all this. Okay, those you should scrutinize properly. Now let's say, now the results are created. What do you want to see? S parameter results, right? So in the rectangular plot, you can see Smith chart and all these different types of results you can create. You can even create equation with the results. For now, we'll see this. You have to see, just click and then bring here. Once you bring here, you see it shows all the results created by this simulation. So S11, S22, S33, that we will see now. We click here S11, S22, S33, then add, and then shows which type of data you want to see. dB, dBm, magnitude, phase, all these times, different types of data, different types of visualization you can create. Generally, we see S parameter we see in dB, right? So this S11, that means how good is the matching we want to see. So, okay, see this shows. Now you see here, the S11 matches very close to 3 gigahertz. And S22 and S33 are also below minus 30 dB. Okay, all these things, all the data are below minus 15 dB. And S11 particularly, it matches close to 3 gigahertz. So now remember, we have used the line cal tool for 3 gigahertz to calculate line and all this, line parameters, widths and all. So that is now verified through the design, right? That's how your accurate is the line cal tool. Now let's say, so now that matching is done, what we want to see is the power division. Is the 3 dB power is getting divided into port 2 and port 3? How do we see that? Let's say we move on here, we create another window. We can see S21 and S31. That means dB. Okay. Now you see here. What do you see here? Both the results, if you input in port 1, what you will get at port 2 or 3. Both of them, you see, it is within 3 dB, plus minus 0.5 dB variation. You know, although because the scale is small, it shows like a big variation. But if you see the values here, you see it is only between 0.3 to 0.7. That is what you will get practically. Okay. So it is very close to minus 3 dB. That means your power at port 1 is divided into port 2 and 3 by 3 dB, 3 dB. Half power is getting to port 2 and half power, that is a 2-port power divider. That is how Wilkinson power divider works, right? That is what we saw yesterday. Not only that, this is the amplitude. One more thing you can see is the phase. S21 and S31, you can see the phase also. You know, see now there is a how much phase difference. Both of them, you see, they are actually overlapping. That means both of them are actually in same phase, because they are kind of, you know, symmetric. Both the ports are symmetric compared to port 1. But if you go to branch line coupler, you will see there is a phase difference between the port 2 and 3. Okay, that you will not have here. So, but the point is, you can see both magnitude and phase. And the same thing you will see if you actually fabricate this Wilkinson power divider and measure through the VNA, you will see the same results in the VNA. Okay. The main thing is we want to ensure that 3 dB power, it is very close to 3 dB, S21 and S31. And the other thing is the matching must be good. You know, generally it should be below 20 dB or 30 dB. That is also what we are getting. Okay, now at this point, I will ask if you have any question. Yeah.
Sir, actually for 50 ohm, 50 ohm line, whatever we have used at the input, so that phase should be selected. We can select 0 also, sir. You have taken 180, I think. 180 or 0 is same only, right?
180 and 0 is no. See, the 50 ohm line, as I told you, no, the phase does not matter generally. Just for the port connection, you need some length. Okay, that generally you can, you know, do a tuning to see what gives you optimum matching.
We can take any length, sir, or any specific.
You can take any length, yes, as long as your matching is good. It does not, you know, for your design in the Wilkinson power divider, design parameters does not say anything about 50 ohm line length. That you can take of your choice. Yes.
Okay, sir. And one more thing, when we have seen the 3 dB loss, it is coming around 3.4. So by practically also, when we implement the circuit, we will get 3.4 or 3. Generally, it will be 3.
Yeah, see, generally this is very good. You won't get this much good. It might go up to 4 dB also.
Okay.
Yeah. It might
But
actually go to 4
generally,
dB.
people say 3 dB will be coming, na?
That is theoretical, right? So, but that's why we are doing the simulation to see what is the difference between theory and practice, right?
So, sir, when we purchase this mini circuits and all, it will be like 3.5 only.
No, so those things you might be using a Wilkinson power divider, or I mean, sorry, you might be using a what do you call the waveguide power divider, right? Generally. So
Okay.
those will have a better power because this does not have a substrate like this. They have they are based on very good metals, right? They might have
Okay.
3 dB, very close to 3 dB. But when you do a substrate based design, this might be the problem because of loss and all. FR4 is a lossy substrate, as you know, right?
Okay. Okay.
Yeah.
So if we
If you
go
know,
RT-Duride or something, it
yeah,
may
yeah,
improve.
it might be
Okay.
better.
Okay.
Yes, yes, yes.
Sir, I have one question. Oh,
Mhm.
okay, sorry. Yeah, continue.
No issue. And
Okay.
one more thing, sir, this is tuned only to 3 gigahertz. If I
Uh-huh.
want from around 5 to 10 gigahertz, I want 3 dB means it should be matched. Means what should I do?
You should take the generally the center frequency of your band.
Okay.
Yeah.
And how
Okay.
much loss I may expect at band edges? Any idea? Okay, I will
See, the
simulate
thing
and
is, if
yeah.
you go to higher frequencies, the losses will be more. So that's why you need better substrates. Yes.
Okay,
So how
sir.
much I cannot exactly tell you. That's why you have to do the simulation and see yourself.
Okay, sir. Okay.
Yeah. Next question. Yeah.
Yeah. Sir, I want to ask, like, why are we terminating the circuit with the 50 ohm, like both all the three ports? Like a
Yeah.
generic
Yeah.
question.
Yes. Yes. Now you tell me how S parameters are defined. What is the definition of S21? What do you tell? What is S21?
It's basically what the input is giving at port 1 and taking the result out at port 2.
Yes. But what about port 3?
Uh, we don't want to like port 3 to be considered.
No. That is what you are missing. You should see the definition carefully. It says all the other ports should be terminated or matched.
Oh,
Yeah, that is the
okay.
definition of S parameters. Yes.
Okay, so this is kind of a matching. Like when we are
Ah,
measuring S21, so it is going to okay, right. It is going
we
to
are
like
yeah. Mhm.
terminate it. Right.
Yes, we are
Okay.
ensuring there is no reflection from the other ports. That is how
Right.
S parameter is defined. That's why we are using this. Yes.
Yeah. Thank you, sir.
Yeah. Yeah. And the
So
same
in
thing, not
the
only this, the hardware perspective also, if you fabricate a board, multi-port board, you'll see yesterday I was telling somebody that, if you have a 3-port board, you have to actually terminate the 3rd port if you want to take H21 because
Right.
definition tells here also same thing. Yes.
Okay. Yeah. Got it. Thank you.
Yes.
hello.
Yeah.
Doing three-way power divider same procedure you have to go.
Sorry, come again.
We are doing two-way power divider.
Mm-hmm.
For three-way same procedure or different way any?
Yeah, it might be different for a different circuit. Are you talking about different circuit? I did not understand.
No. For this only, by extending the second line,
Mm-hmm.
we can get that with three-way power divider.
No. It is
How come?
not so simple. You have to design, you have to look into the design itself. That is a defined design itself. Okay. No, it is not like that. Yeah.
Hello.
Yes.
Sir, here we are designing the microstrip line above the substrate, right?
Yeah, right. Yes.
So for example, if I have a unit cell and on top of that substrate, I have created a patch. Now I need some kind of power dividing or power coupling to be done beneath the substrate at the bottom layer through microstrip lines only, and that is to be matched to 50 ohm. And below that microstrip line is a spacer, air spacer. Let's take it about 12 or 14 millimeter. So in that case, in which the microstrip line is to be designed at the bottom of the substrate, how will we go about the specifications of M sub and the T line calculation?
You mean your substrate is not directly grounded, or it has a air gap or something?
Yeah. So, like I'm taking a substrate, on top of it, there is a patch. Let's say circular patch, okay? And at the bottom of the substrate, we are having a power dividing or power coupling through microstrip lines only, which is to be
Okay,
matched.
that is
to
no,
50
that is fine. Where is your ground? Yes.
Ground is beneath the transmission line. There is a 12 millimeter, 14 millimeter air gap. After that is the ground.
No, so that's means.
So in this M-sub and transmission line calculation, how will we go about that?
See, if your substrate directly has a ground beneath it, it is simple as this. Okay. So what I understand from yours that there might be air gap between antenna and ground, but the ground is directly connected to the power divider circuit, right?
The ground is not connected to the power divider circuit. There is an air spacer between that. That's
no,
what
no.
I'm
Oh,
trying
okay,
to
okay.
ask.
No, no. See, no, no, no. That is not the way microstrip line will work. Microstrip line directly says it should have a ground in the bottom. Okay. Yeah, it should. You must have a substrate ground for the substrate.
The microstrip line should be connected to the ground layer. That's what you're saying.
No, 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 no. Microstrip line definition is that. Microstrip line definition is, if you remember your studies thing, it comes defined only as that. It must have a ground at the bottom, and at the top layer we have a patch. The metallic patch.
Actually, I came across a paper in that the design was something like this. So I was trying to mimic it over ADS. So that's why I asked you this.
So you see, I don't know exactly. If you have something like that, so what you can do, you can calculate a effective permittivity of the substrate of the composite air and your substrate. You have to calculate a effective permittivity, and that you can put here.
Even though the microstrip line is coming in between of those two.
Let's say it comes, even though you can try with that. You can try with effective permittivity. Okay. So now we'll move on to the next section. See, now the thing is, we have done a schematic, but as I told you, schematic is not perfect, right? We have to do 3D simulation. So how do we do that? We have to move on to the next section. Now you see here, if we just, bluntly we convert this to layout. Okay. Here you option have generate update layout. All this section, let's say we do okay. And you see like what we have got. See, but this is not a Wilkinson power divider, right? It has got all jumbled up, all got overlapped each other. Why this happened? Because if you see here, we did not take any bend or T junction or nothing. It's just a idealistic, simulation. That's why you will not get a good layout here through this. Now we have to move on for that. Okay, next we will go to that. Let's see. We'll show you how to get a good layout also. We'll create another schematic first. Now let's do this. So the same parameters I will define here for a 1.57 millimeter substrate FR4. The same thing, but I want to now do a 3D simulation. Okay. Now that these are defined, let us define some variables now. So why these variables are required? Let's say you have now 10 components and 10 microstrip line you have to define all the time the length and width and all, but many of them are common, right? So you can define a common variable and then use it for everybody. So what we'll do now, let's say we define first is W50. That means thickness for the line, 50 ohm line. So that will be 3.06. Okay, add. And next we take W70. That is 1.6. See here, you note that no units are being put here. So those units you have to add in your actual microstrip line thing there. Okay, there I will use the units. Add. We'll take different lengths now. Let's say take L2. So it will be soon clear why I define so many components. Okay, let's say for now we take this 4 only. It is not shipped. Okay, again I will do. Okay, now that it is applied, so here we will do some other thing also. So you see, there is option of tuning. Tuning means you can change. So sometimes, the what we get theoretically or mathematically, those will not be exactly valid, right? So oftentimes we have to tune because of this parasitic effects and laws and all. So this tuning you can do is a very good feature in this software. So first thing is you go here, this parameter, let's say I want to tune the length of the lines L2 and L4. You go here in the tune, enable it, and then you want to see like in which steps you want to. Let's say we don't touch that, but we enable the tuning. See, once we enable it, you see it shows it can be tuned. Okay, it will come soon. Apply. See, within parentheses, it shows T. That means it will be tuned now. L4 also, let's say we tune it. Enable it, okay it, apply it. Now it's done. Okay, so that means when you do the simulation, you will have an option to change these values and see where you get your perfect results. That is very, it's a necessity nowadays. So let's say now that these are defined, we now go with a actual design, okay, of Wilkinson power divider. So it will require a lot of components. We'll go into that now. So this is as usual W50 port line. Length, let's say we take as okay. Now what we need is a T junction between these two lines. Okay. Okay. First we will define this also. This will be W70. Length will be L2, let's say. See here I have forgot to, change the line unit here. That you have to always do. If you don't do the unit carefully, it will not come because the variable I have defined without units. You can do it there also, vice versa, both are fine. Now let's say I copy this and copy it here. There and then what else is required is this is, let's say, L4. Yeah. So soon you will see why now so many components are required. Previously we did it's only few, but that was not a actual design, right? You will see now why it is required now. So empty, okay. We'll take empty here. Same empty will be required here as well. See in empty, the vital parameter is how you define the width, line width. So it will depend on that. Okay, I will soon, let me just complete, I'll show you. So if I go to help, you see here they define this 1, 2, 3, and 1 is given with a cut. This 1, 2, 3, as you see in a clockwise version. So you have to define the line width properly. So if you don't do, then how this 50 ohm line to 50 ohm line, 70 ohm line is connected, that will not be done properly. So here, as you see, I have 50 ohm line this side. So this is here port 3. This is the 3, clockwise 1, 2, and 3. So that's why this W3 is W50. And on the top and bottom, I want to connect a 70 ohm line. So that's why you see W1 and W2 here is W70. So that is what you have to take care. So if you don't do this properly, you will always get a error. Okay. So always take care of that. Similarly, let's say we want a bend here as well. We want a T here as well. So here, what do we want? We want a 50 ohm line this side. So that is done here. Similar thing is required here as well. Okay, before going there, we need now what we need is bends or the curves. Okay, we'll take M curve. So this curve will be W70 definitely because it will be connected to W70. Angle is 90. This now radius of curve is actually, it's a parameter. You have to define carefully. Now let's say I define it as 4 millimeter. Sorry, this I will take as a 1 millimeter. So even see this also you can take as a parameter and tune it R1. Okay. So this is there. Now what I do, I just copy here, and copy here. Now you see, now does it look like a connection or not? So soon you will see how it actually looks like. Okay, so this are done. This T you can connect here. Okay, this T is done. Now what is required is 2-port cell. This is a 50 ohm line. This is for port 2 and 3, and we will take some line length here. The advantage in this design is, as you see, because this is symmetric, once you do it, you can just copy paste in the other half. One half you do and second half you just copy paste it. Okay, not only this, now we have another bend required here. See here. Let's say this will be W50 millimeter, angle is 90 degree, and radius of curvature, let's say we take it 4 millimeter here. Now see, I guess all the designs are done, but we want to proceed to layout. Okay, now we are not going to do in schematic simulation. So schematic, as I told you, in layout you cannot add the lumped components like capacitor, inductor, all these things. So the space for resistance we'll keep it blank now. We'll define the ports here. Port 1, the pins, port pins you can define like this. Port 1, and we define port 2, port 3, and this inside also we define 2 ports. Why? Because in between these 2 ports we will define the resistance. So if you keep something blank, that you have to replace with something else, so that you can put it for the connection. So that's why I am keeping 2 different extra ports here, because ultimately I have to put a resistance between these 2. Okay, now that all these things are set, port 1, 3 ports I have defined for port 1, 2, 3, and extra port also just for the resistance connection. Now all this you see, now let's see if we have done it correctly. Let's generate the layout. So the thing is, see, there is some problem. Although it came because of a small problem, it went different ways. So we will rectify that. What is this line?
I have
This
a
is
question, sir.
sorry.
Can I ask? I have,
Just let me
okay.
complete this, then I will take. Yeah. TL3. Let's see where is TL3. Okay. See, here you see, I have missed the unit. That's why it was coming. That's why the units are very vital. You have to put carefully. One miss and you are gone. Okay, now let's see. Let's generate the layout. Now you see how beautifully it has come. This is what we want, right? Yeah, some 1-2 questions only I will take. Yeah, ask. Yes.
Yeah. So once you calculated the length of the microstrip line using LineCal, so it was around 14.25 mm. But when you use the like MT and M curve, then you use the length of the line as 7.7 and 2. Why it is so?
Yeah, because see here there are multiple bends, right? These bend lengths also you have to take care of. Okay, now the thing is you cannot actually theoretically calculate all this length. So that's why you can take some lengths, and then I have kept you remember I have kept a function for tuning. Okay, so you can actually tune there the length, what is actually required to get the parameter. So that's why this tuning is vital. Okay, I will show the tuning function once, then you will understand. So now you can tell like how I am getting these things. Even the the bend radius, I have already done this before to show you guys, because if I have to do everything from scratch, it will take a lot of time. So I have actually tuned these parameters. Okay, but if you actually add all these things line together, then it will come around 14. Now let's see. If I will show you without the ports here, let's quickly do once the S parameter simulation itself. What will I do? Let's go. I'll show you the how tuning is getting done. Okay. So as well, just as the last schematic, we define the terminator here, port terminations, and then we terminate with this and this ground. Then when all are done, let's now simulate. Simulate in the schematic well only. Okay, so all these are designed. Now see what we get. S11, S22 and S33 quickly, TB. Okay. Okay. So you see we got a very close response only. That means it's matched with the previous ideal response. So you see that is what we wanted, right? As good as the other one. Now you see the thing is, if we don't know these lengths, right? You take some arbitrary length, I mean very close length, because you see L4, if you see here, this length and this length together, as well as this bend lengths, together should be lambda by 4, okay? As well as this T length also, T width. All these things, actually you cannot, calculate all of them together. At least these two lengths, that you add, and this here you see L2 and L4 is around 8. And the radius of the bends, it adds a length. So together it will come around something around 12 to 14. Okay. Now how you will know? Because you see we have added this tuning function here. So you will see now how we do. You click on this tune. Now you see beautifully what happens. We'll do a this is from the last time. We have to first open the window that we forgot, open the results window. Okay, that will open first. I guess I have saved it. Cell 1 is except okay, cell 2. Now that this result is there, let's do the tuning once again. It gone. Huh. Okay, now see the length L2 and L4. What are these two? This is this line, this line and this line length. I have tuned. Okay, you can actually change and see what are the impact in the results. Now see, as I change, you see the results in the right side window how it varies. Just by tuning this length, you can adjust in which frequency you want the good response. Is it very clear to you? Because this is very important feature, because many of the times you will not have the ideal length or whatever parameters required. Then you have to take some initial guess close to it, and then you tune these parameters. By tuning it, you see, we can shift it to other frequencies as well. So that is what you have to do. That is what I have also done. So now you can tune it and then save the parameters. I have already tuned it, so I am not doing. Otherwise, you can save it. Now that is how first you have to do tune and get the best results in schematic. Once that is done, now you can move on to layout. That is what we go to now next. So layout means, as I told you, you have to remove the resistance here, or maybe I will take another one. Let's say I take another cell here. That will be more useful. Cell 3 I take. Can I just copy paste here? Let's see. Okay, so now I have copy pasted the same schematic here. What I do, I delete the resistance because that cannot be included in the layout simulation. What I go remove the termination here, 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 everywhere. Remove the termination. That is all done. what we do is we get the ports. These port pins are very important. You can add here, you can even add in the layout as well. That is there, but I find it easier here. Now these ports are defined. Once again, we'll go to generate the layout here. So it's simple. You don't have to do any changing here, any setup changes. You just do, and the layout is generated. Now you see you have come back to the PCB domain. Okay. So this is, if you just give this as a Gerber file to your manufacturer, they will print on top of the substrate. This is, as realistic as it possible. Now you see here the ports are defined here. You see port 1, port 2, port 3 defined as the the arrows here shows the ports, and in between we have kept a gap for the resistance. We will be connecting the 100 ohm resistance here. So as you see, even a simple Wilkinson power divider as it looks, to make it actually realistic, you have to do a lot of things. You have to add the corners and bends and all. Now let's go to the next section. Where do you go? We'll go to the EM simulator tool. In the EM simulator tool, you see the ports has been defined. It's showing, they see there are so many problems here. It is showing the yellow alerts. First, you have to define a substrate. Let's do a substrate. So it shows the substrate here. By default, it's alumina. We have to change. See, click here in the substrate model here, and then you can select from the parameters here. Or you can just add dielectric also. Let's say I add a dielectric here. Let's say I name it FR4. You can find from the library, as well as you can add your own dielectric. So I am adding here. So 4.3, 0.025, all these things I have defined. So now this all okay is done. And thickness is, let's say this metal thickness I want to take. Okay, that is there. That is all fine. Okay. So the dielectric thickness also I have to define. How much is, we wanted 1.57 millimeter. So these two ones done. Now we are towards the 3D EM simulation. These parameters all are required for 3D EM simulation. Okay. So now you see materials FR4. So FR4 substrate 1.57 millimeter. Shape done. See, those are all defined now. FR4 and all are done. Now you see all the yellow alerts are also gone. So see, there are different type of simulations available. What we want is momentum microwave, but there you can also use FEM or momentum RF. Those solvers are also there, but mostly what is useful for our microwave is momentum microwave. This we will do. Layout, all these things are there. Substrate is defined. Okay. Ports are all defined. Frequency plan we have to select now. We want it between, let's say, 2 to 4 gigahertz. 2 to 4 gigahertz. Number of points, let's say we take 100 points. See, all these things, there are different things, but not all of them you have to actually, change. So this auto create EM model you can click on, because every time you launch it, it will create the same EM model. So now the thing is, the main vital parameter is MES. MES, to simulate 3D simulation, like FDTD, method of moments, anything, you require to, define or divide the whole surface or the volume into different parts. Those are called MES. That is how 3D simulation is done. So that once you take, we'll take generally cells per wavelength, lambda by 20 meshing. That is okay, by definition is fine. Even transition line males also you can take 20. For better results, you can actually take a 30 or 40 or 50. Okay. But the thing is, the number of meshings as you increase, it will give you a very good results, but the simulation will also take a lot of time for that. and see generate S parameters we have defined. All these things are done. Once all these things are done, you can simulate. So only thing you should see the transmission line mesh and mesh density. Otherwise, automatically it will be there. You just see when the mesh is not there. So you will see the mesh view once. See, once the mesh is created, now you see. This
between
you see.
Two ports between 2 ports, 100 ohms must be there, na? We have to
No, not here. That is, if you should listen carefully. I told you in the EM simulation you cannot add lumped components.
But in ports we can add, na? Ports, port this and this we can add.
That we will come to. We will come to in the core simulation. Yeah. So now the point is, you see the meshes. You see the now the fine lines it shows. The electric and magnetic field, current density, all this will be created on this mesh. And as you see on the edges and corners, you see is very dense because there the calculation is much more required. Very crucial calculations will be there in the meshes, in the edges, because there will be change will be very sharp in the edges. Otherwise, in the normal lines, you see their mesh density is very less. So now that all this is done, we'll go once back. This has been done. We'll go to EM simulation once again. We do S parameters and simulate. See, now it is simulating. So look out for all the warnings and all. Some of them will not be useful. It will be just, by default it shows. Other things will be required. So it takes some time. See, it takes some time for 3D simulation. As you know, in CST, HFSS everywhere. But schematic simulation will be done within a second. So just wait for it.
Can I ask a few questions if it's fine now?
Yeah.
One thing, like in the substrate definition, I guess the conductor width, like conductor height of which is 35 microns basically. So that was missing, if I'm not wrong.
Oh, was that missing? Okay. So generally, yeah, it will be like close to that only. It should not matter that much. Yeah, but I guess there will be. I might have missed it. You can define that also.
Okay, and that is one thing. And secondly, if you're placing a resistor, so resistor is also having a fixed pad size, like let's say it's 0402 or 0603. So that thing we need to take care over here, like using the transmission lines only, or there is a different like pad editor or something of that sort.
No, yeah. So yeah, that is also crucial. If you actually go to, one way you can do is that, you can create this gap here between the ports such that it will be actually given what is in datasheet. Okay, that is how you can do. And otherwise, you can take a pad also here. Okay, that microstrip pad lines are also available in the components.
Okay, so it is available like specific to pads. That is also available.
Yeah. See, now the simulation results has come back. So as you see, the results are like quite different. But this is not the actual result we want because the the resistance is not connected here. Okay. So now we'll go to the save the results. Okay, so there was no errors. It's fine. That is all fine. So now we are creating a symbol here. From the 3D simulation, it is very vital to create the symbol. Symbol means it will take the data from the 3D simulation and bring it here. Okay, you have to click lookalike. Okay, and all the other parameters are fine. Now you see what we have got. Okay, so it creates the same lookalike file. I mean the hardware, But ultimately it has multiple ports, and these ports actually take the EM simulation data from the 3D simulation. So the steps, if you remember, as I have shown you before, there are 3 steps. First you do in schematic, remove the lumped components, go to layout, and then come back to co-simulation for final results. Okay. But one thing, the tuning you can do only in schematic, you remember. So before going to layout, you can do tuning here. And when you see these results are very good in tuning, then you can remove the lump components and terminations and all and go to layout. Now let's see what we do here. Here what we do? We do the same thing here. We connect the resistance here basically. Okay, we will save this. We create another cell. Okay. Actually what we have to do, we have to actually import the symbol. Let me see. You can just copy paste to the I don't know. There was another option for importing that I might have forgot. But yeah, this way also it works. That's fine. So just simple copy paste also fine. So the thing is you have to bring that symbol to your schematic file. That is what is required. And now here, as usual, you define the resistance here. Dead ohm. And the port 1, 2, 3 has been defined, but the thing you have to give the terminations here. now that all the ports are defined and all, see it looks small, but actually where you define the port, there only you define the at the termination. Yeah, terminal 1, 2, 3 are there. Same again, you define the S parameter here to 4 gigahertz, 0.01 gigahertz, apply, okay, and simulate. Number of nodes, okay, let's see if what we get here is 1. Okay, so that means there has been some problem here. Let's see. I guess this port has to, I see. So as you see, there has been a problem in the port definition. That's why, these things are not getting, and this, okay. So this means this ports I can define here. Let me see. There was an easier way to import. Let me do it once again. So the schematic is there. Yes, and the new schematic. Oh, I have answered the screen. Okay. So now let's see the schematic I get here. Okay. So there has been in cell 3 I browse. Take one. Okay. Cell I cell 3. Okay. Somehow the thing is, double resistance has been created here. I mean, double ports. That I am trying to figure out why. Okay, so that means number OTC. See, the warning message are very important. That's why it says there has been problem in connection. Okay, so I have to go back to the previous one. It seems. No. Might be some problem here. Four and six. Okay. Yeah, hopefully it will be correct this problem. Let's see. Okay. So that seems that there has been some problem in the layout itself, maybe, I suppose. So sometimes the spins create problem. So I have to redefine the spins. Okay. I don't know. Somehow. Okay, let's say it has been a problem in the layout itself. I will delete it and create a new one. Sometimes, deleting the ports here and adding in the layout directly will solve. So let's see now. Without any ports here, but we can add the ports in the layout also. Okay, so that we will do now. Even okay, that also was there. This ports will delete. So see here you have the blue dots here, right? So you can directly add the pins here itself. That is another option. Let's do that. So I suppose because there was a problem in that one, that's why it was causing something.
Sir, your screen is stuck in the main window. We are unable to see other windows. It is stuck with the main workspace window.
Oh, is it? Main. I see. Okay. Sorry. Yeah, so what I'm doing is, see, I remove the ports from the here, schematic. Sometimes that creates problem. So I wanted to, add ports directly in the layout. You see here, it will show blue dots like that. Here you can add your ports directly. 1, 2, 3, 4, 5 ports. I have added ports. And okay, now that all these things are fine, I will do the setup was ports are there 1, 2, 3, 4, 5. Output plan options mesh will reduce simulate. So let's resimulate and see now. Okay. Save. See, as long as it shows here red, that means the port has not matched perfectly. So you can actually, you have to maneuver a little bit to match the ports perfectly.
In port tab, we can see that every port is a 50 ohm.
Sorry?
In port, in while simulations, while go to ports, in every port it is a 50 termination. Once see the once check it.
Right.
Once go to that port tab, so by simulation you can go on.
Yes, you are talking about EM simulation?
Yes, EM simulation.
Yeah.
Here ports.
Yes. Ports, yes.
Then after port 5 and 4, you can make it as a, it is already 50 ohm termination, impedance is 50. You can make it as 4 and 5 as 100 ohms by merging, removing that ground at 4 and 5 ground remove. Then port 5 go to that port 4, then make it as 100 ohms both.
Okay. So you were saying okay, that I see.
Delete that ground, sir. Port, what is that ports once check, sir? Once check that port, sir. Don't
Port
delete
1.
that port 1, sir. Port 1 is already, it is a initial, no, sir. Once check that third and fourth, once check that ports, sir, at EM simulation.
I see. What you were saying that ports are already defined, right? That is what you were saying.
It's already defined it as the 50 ohms.
Yeah. So I may not need extra termination, you were saying.
Extra, it is not necessary.
Yeah,
100 ohms also remove, sir. 100 ohms also. Here 5 and 4 is 100 ohms we have required.
That is there, but no, I know that it can be done here also. You can just do you can add 100 ohm also as well. Let me see.
Then port 4 and port 5 remove, sir. Then it will possible.
There you were saying.
Now simulate site possible.
Let's see.
Yeah, it won't simulate with the terminations. Terminations are necessary.
Yeah. That is what I was thinking. The terminations are required generally.
Yes.
Then like this only do, sir. Then make it port 4 and port 5. Then make it on that port.
Yeah, let me see. Try once more. Otherwise, I will find out and let you know tomorrow. Okay. Might be some minute problem. I don't know. Sometimes, it happens.
So probably there is some issue with the symbol. Like, did you drag and drop it in the schematic, or did you copy paste from the symbol page? Like for this simulation.
Copy pasted.
Yeah, so please try dragging that symbol into the schematic. It might there might be issue there because ideally this P1, P2, P3 shouldn't appear in the cosine option.
Yeah, right. Actually, yeah, that is what I was thinking. That should not actually appear. Yeah, that is what you are right. Yeah, I don't know.
So you have opened an EM co-simulation or EM only?
Sorry, I have.
No, EM, EM co-simulation only this thing is possible, na? Resistor and all.
Yes.
But
yeah. This is same, right? The window what you have, it will not be defined, right? This is normal schematic window you will have.
No, we have to open some other EM co-simulation application and there we have to call this symbol or.
let me see. Let me see. Let me see my previous ones. What I have done. Okay. Yeah, see, this will be like this, normal semantic only. Yeah, but what he has said is right. This the port should not be there actually. Yeah. Yeah.
Yes, exactly. Every
Yeah,
course you
yeah,
have to
yeah.
remove.
Yeah, yeah. So these ports, it will be like this only, but somehow I don't know why it is not coming like that. Yeah. Maybe I am not doing it correctly now.
Please try the drag and drop option. It should work.
How is
Instead
it?
of copy pasting.
Yeah, let me see. Yeah, yeah, it is coming, right. Yeah, right. Thank you. Yes, yeah, this is what I was actually looking for, because it should not come with the ports. Yeah, right. Yeah, right. So now that ports are defined, let's change 2 to 4. And some.
The connections are not met. It is still.
Yeah. So should be now, it should be fine. Let's see. ADS schematic is 0 piece. Okay. This is strange. Let's see. I'll create in the same cell itself. Let's see without the. It seems like there is some strange problem. Okay, so I guess today I will end it here. I will figure it out and maybe I'll show you later. Okay. So yes, something is there, some problem is there. We are almost there, but some minute problem is something happening. I don't know why. Okay. So it might, it might take some time, to figure out why this is like this. Some port has been missing somewhere, I guess. So I will like figure it out and maybe show you in the next class. Okay, next Saturday morning or Saturday afternoon, that I will let you know. Okay. Yeah. But so far as I guess you understand, and you can go through the schematic ones and layout also you can generate and see for the branch line coupler. And I will figure out myself what is not happening here correctly, and then we'll let you know. Okay. I guess I will need some time and thinking clearly what is not working here. So yeah, that's for today. I will end it here. I also have to do something, go somewhere. So next Saturday I will again show you this portion. Okay. Yeah, if you have any question, yeah, you can tell. Yes.
So actually, any mail will come on classes, or regularly we have to check on Saturday, like
no, yeah,
10:30.
regularly. Regularly we'll follow this time schedule only. Saturday, Sunday afternoon only. Okay.
Same link we can use it.
Yes, same link. Yes, same link. But as you told, you can create a WhatsApp group and circulate, and maybe let me know. I will circulate among others. Okay.
Yes, sir.
Yeah. So this is just a small step I am missing somewhere, that I will figure it out and let you know. Okay. Because just hurrying now will make it worse. Sometimes some simple thing will be missing somewhere. So I will figure it out and let you know later. Okay.
With this
So
basics, we can do three-way power divider also.
no, three-way power divider. Yes, you can design yourself. Yes, that is it. Yeah.
With this
Schematic
basics only.
Means one port means other port, like port 1 is the input, port 2, port 3. At port 3 we can use one more power divider, two-way power divider, and we can continue like that, sir. So on.
Yeah, you can continue, but that will not be very efficient actually. Generally, that also is option, but there are other better options available. That like input divider, and there will be like as I told, Geisel power divider. There's many different kind of options are there. That will not require multiple branches like that. I mean, multiple branches obviously will be there at the output end, but if you just stack it like them, they will not be very efficient.
Okay.
So okay then. So I will end it here today, and I will meet you next week Saturday. Okay, I will figure it out, and if it's possible, I will like post it and see. But in between, in meanwhile, you can carry out
Yes, sir.
yourself. You can test in the using the schematic itself, and you can also figure out. I guess I am doing some very silly mistake, that you are welcome to figure out and post in the group. Okay. Yeah.
Yes, sir. Can anyone take anyone have exposure of this WhatsApp creating through Teams? They can create a group.
Yeah, you can create a group. I don't have any problem. Yes. Yeah.
Yeah, someone I am not
we
aware.
can create it in the next class, because maybe like attendance will be higher that time, 80, 90 people are there. And direct in this meeting chat itself, you can post so that everyone will join from here itself.
Yeah. That will be good. Yes. So okay then. Yeah. Bye. Good night. Okay.
Yeah, thank you.
Thank you, sir.
Yeah.
Thank you, sir.